Hi students, welcome back to the class. So in the statistical mechanics, in the last class we were stopped at the molecular energy distribution, and we have the molecular energy distribution n of epsilon d epsilon, that is equal to 2 pi n divided by pi kBT all raised to 3 by 2 root epsilon e raised to minus epsilon by kBT d epsilon. Now today we are just discussing about the extension of last class, that is the average molecular energy. Okay, so we want to know the average molecular energy. Average molecular energy. So the average molecular energy, for example, if you have n number of particles, then what we are going to do, first we will calculate the total internal energy of n molecules. Then after that you divide the whole total energy by the number of particles. That will give you the average molecular energy. So how to get the total internal energy of n particles? So in order to get that, what you have to do, you have to take this molecular energy distribution n of n of epsilon d epsilon, then multiply this with the energy epsilon, then integrate for the whole the energy from 0 to infinity. So that is the total internal energy E is equal to integral 0 to infinity epsilon n of epsilon d epsilon. Okay, so you can substitute the corresponding terms for n of epsilon d epsilon, that is this one. Okay, and I'm not going to repeat it again, so you just rewrite it here. So what you will get, I will just write the final form that will give you 2 pi n, just take the constants outside, all raised to 3 by 2 integral. Then what else you have? There is an epsilon here, there is a root epsilon from this term, so you will have epsilon raised to 3 by 2. Then what else? Then e raised to minus epsilon by kBt d epsilon with limit from 0 to infinity. Actually this term, like the previous case, this is a special integral, and this is a kind of gamma function, and it has a standard value. That standard value is coming from like 0 to infinity x raised to 3 by 2 e raised to minus ax dx is equal to 3 by 4a 4a square root of pi by 8. So this is a standard integral that we are going to use in order to evaluate this integral. Okay, so this you just compare here, compare these two. Here instead of x you have epsilon, and instead of a you have 1 by kBt. Then what you need, so 3 by 4a root pi by a. Okay, so we just substitute it and you will get the final answer as 2 pi n divided by pi kb t raised to 3 by 2. Then here 3 by 4a, 3 by 4a means 3 kBt by 4, because a is 1 by kBt. Then inside the root you have pi kBt, so that will be your final result. So you can write 2 pi n by pi kBt raised to 3 by 2. Then what else? You will have 3 kBt raised to what is called it will be like 3 kBt by 4. Then one term is coming from this root, so you will have 3 by 4 kBt square into 3 by 4 kBt square into square root of 5 kBt all raised to half. Okay, so this is the term that what you are getting, and if you simplify it, you will get a term 3 by 2 n kBt, where kb is the Boltzmann's constant, and you know it is 1.38 into 10 to the power minus 23 joule per Kelvin. Okay, so this is the term, this is the total energy. Now what you need? You need the average molecular energy. In order to get the average molecular energy, you have to divide this total internal energy of n molecules divided by number of molecules, that is you have to divide by n. So the average molecular energy is represented by the symbol. I'm just writing it here. I'll just resolve this. Epsilon bar. So this is the average molecular energy. This is equal to E by capital N. So that is equal to 3 by 2 kBt. Okay. So this will give you the average molecular energy. Okay. This is about the average molecular energy. Now we will go to the distribution of molecular speed. So how we will get it? That also we will take it from our energy distribution, that is N of E d epsilon. So now what you are going to do, you are just taking your energy as a kinetic energy, that is half mv square. So from that one you will get the distribution of velocity for the molecules. Okay. So here again you write the expression for n of epsilon d epsilon, that is equal to, you have an expression, I am not repeating it again, and you can so what you need now, you need molecular speed distribution. So this you need to find out. So the energy of a molecule, I already told, we consider only the kinetic energy. So that is equal to half mv square. Now what you need? You have the energy distribution now. Now you want the speed distribution, the distribution of molecular speed that you need. Okay. So instead of the energy epsilon, you have to change it to velocity. That is our purpose. So here you can write d epsilon is equal to half m 2v dv, or d epsilon is equal to mv dv. Okay. So this is the situation. You can now replace all the epsilon in your equation with this half mv square, and all the terms d epsilon by this mv dv, that we are going to do. So I will just rewrite the n of epsilon d epsilon again, so that will give you n of epsilon d epsilon is equal to 2 pi n pi kBt all raised to 3 by 2 root of epsilon d epsilon. Okay. So this is the sorry, I forgot the exponential term, that is e raised to minus epsilon by kBt d epsilon. So this is the energy distribution. Now all the epsilon is replaced with half mv square. So here you have to change, here you have to change, and d epsilon by this one. So I just you can do it at your home, and I will just write the result here. So what you will get it after that? You will get n of v dv is equal to After doing all the substitution properly, you will get 4 pi n. Then you have to write m by pi kBt all raised to 3 by 2. Then you will have v square e raised to minus v square by m minus mv square by 2 kBt then dV. So this is the distribution of molecular speed. Okay, so this is the expression, you can check it properly. Then from this one you can find out the distribution of speed or the molecular speed distribution. And once you plot this n of e dV versus the velocity, you will get the plot like this. You will get, this is your velocity and this is your n of e dV. So the plot will be somewhat, that will be a somewhat like this. Okay. So if you plot, that means if you are just taking this n of e dV on the y axis and v on the x axis, then you will get something like this. And here the value where you are getting the most probable, so that we call it as the most probable velocity. So because it has a more number of speed, this speed, whatever the speed here, that is the highest number, so that we call it as the most probable velocity, most probable velocity speed, not velocity, speed. Okay, because we are not dealing with the vector, so we are just looking at the speed. So this is the most probable speed. I am just representing it as Vp, or you may write it as Vmp. I am just writing it as Vp. And after that we will get the average speed. Okay, so before that we will go to the root mean square, that is called the VRMS, root mean square, that is square root of, this is the root mean square, or you write VRMS. And there is one more thing, that is called the average speed that will come in between. So this is called the average speed. Okay, so we average. So this is the 3 different values. So out of this you have to be careful. Your VRMS, this is the highest value of speed, VRMS. Root mean square speed is the highest speed, but this is not the highest number of particles, doesn't possess this VRMS. Highest number of particles possess the most probable speed, and least number of particles possess the VRMS. And average speed, this is the average, that is great, the speed wise, this is greater than most probable and less than VRMS. Okay, but the number wise, this is less than most probable but greater than VRMS. So you can write it as here like VRMS is the highest, then V average, then VP. So this is the trend. But when you are looking at the number of particles, then the thing is just reverse. That is, most probable is the highest, then we average, then we RMS. Okay, so this is the whole thing about it, and you may get the values for the V RMS. Can you see this? I think V RMS is equal to square root of 3 kBT by M. Then what you need? You need the most probable. So most probable VP. VP is equal to square root of 2 kBT by M, and the last one is V average is equal to square root of 8 kBT by pi M. 8 kBT by pi M. So this is the thing. Okay, so I am writing up it here, and now we will go to the quantum statistics, or the statistics for the indistinguishable particles. Okay.